So when you draw the resonance structures for the cyclopentadienyl anion, that's what you call that silly thing. Sorry, I had too many things in my pocket. I lost my fancy stylus somewhere too. This is probably what this is on. Okay. This is what they look like, and the electrons distribute freely around the structure, okay, implying it's relatively stable. And so you can actually do this. Oh, apparently you can't change slides. Very good. Can I change slides here? Yeah. Seem to have broken the internet again. Oh, now it's working again. pKa for cyclopentadiene is only about 16. And when you make it, you can add sodium hydroxide to it and form a reasonable amount of the cyclopentadiene. The resonance structures, the hybrid from what we had shown before, looks like this. That's how we draw it. So it's like benzene, right? Delocalize electrons around the middle and then put the negative charge in the middle. So one of the really cool things that cyclopentadiene does, and Dr. G would be proud of me for drawing this in class, is if you put iron in the middle, cyclopentadiene will form a sandwich out of it. And I say that, okay, and then what happens is each one of these carbons forms a partial bond to the iron atom in the middle, okay? It's kind of one of the reasons why you can tell that the negative charge is distributed in the ring evenly, is that it forms what we call these sandwich compounds. With the iron in the middle, right, and this is -2 total and +2 total, so it forms a stable compound. You can actually isolate that's really easy to make. Yeah, I always thought that was cool. You guys get the sandwich idea? Like the top's a hamburger bun, the bottom's a hamburger bun. If you're vegetarian, it's a portobello mushroom bun. Peanut butter and jelly sandwich with iron in the middle. I don't know. Something like that. All right. So this is, we're just going to go back through. This is the book. I'll just take you through these slides. It's kind of review, but we talked about a lot of this yesterday. If you have a 7-membered ring, right, in order to have it be aromatic, you have to have an odd number of electrons. Oops. And continuously conjugate it. So I'm going to try to draw a 7-membered ring like that. And then I'm going to put in 6 pi electrons. So I'm going to go 2, 4, 6. How do I make that aromatic? You got to remove a hydrogen, but be more specific. I have hydrogen like this, right? I have 2 hydrogens. So if I remove the hydrogen, like say bring in a base, I'm going to erase some of this in a second, so maybe that's an indication that it does that. How many pairs of electrons will I have in the system? So what would that make it? Yeah, it would be antiaromatic. So cyclopentadiene, we can take the hydrogen off very easily, leave a pair of electrons behind. You can't do that with this. In order to make it aromatic, okay, so I'm going to back up here like this. You have to take the whole thing, right? If you can pull the whole thing off, then what you end up getting is this. I'll put the H up there. put a positive like that. You can form that. That's an aromatic ion. So it's a lot more stable than you predict it to be, and that's actually relatively easy to form. Okay? Make sense what I'm doing? Draw the system, right? 7-membered ring. It's got 3 bonding molecular orbitals. I stuck the electrons into the bonding molecular orbital, right? That gives me this system here. In order to be aromatic, I'm going to have to pull a hydrogen and the electron off of it. And that allows it to be aromatic.
So you have to have a carbocation?
For this one.
Okay.
But for we were just talking about cyclopentadiene, you have to have it as an anion because in order to be aromatic, you have to have an odd number of electron pairs. Right? So think about that when like on a test, if I give you a problem, just make sure you're left with an odd number of electrons pairs if you want aromatic. If you want anti-aromatic, have an even number of electron pairs. Okay. Some other aromatic compounds. There's pyridine and there's pyrrole. These are both aromatic. Oh, actually, I've gotten kind of used to not having my iPad, so I've been drawing on the board a lot more. But I like to be able to draw it on the screen. So let me draw this out for you. Okay. So pyridine has a nitrogen there instead of a carbon, right? So what does it have coming off of that nitrogen? Yeah, it's a pair of electrons. So I'm going to draw them out like this. Now, pyrrole is a 5-membered ring. I'll draw it with the nitrogen pointing in the same direction. It looks like this. Looks like that. So it looks like cyclopentadiene, right? What else does that nitrogen have coming off of it? Yeah, it has an electron pair on it. Draw it like this. Now, we've used pyridine a lot in synthesis. What do we use it for? What is it used as? It could be used for oxidation. But yeah, because it can pull off hydrogens. So it's a base. Okay. So we use this as a base. What do you think about pyrrole? Do you think that could be a base as well? And how would you know whether or not it could act as a base? Well, yeah, it depends on pH, actually. That's true. Make it really acidic, right? But in order for that to act as a base, the lone pair has to be available to pick up the proton, right? So, pyrrole, pyridine has a lone pair. Pyrrole has a lone pair. They kind of look the same, right? Turns out pyridine is a base, pyrrole is not.
Does it act as an acid?
It could. But it'd be relatively unstable, I think.
Because of the electron pairs, right?
Yeah, because you have the electrons there. But it's not a base, right? Because the lone pair is involved in resonance. If you invoke resonance in this compound, okay, you can take this lone pair and do this. I don't know what the pK is. I have to look it up, though. All right, it looks a lot like cyclopentadiene, right? So another resonant structure like this. Again, it's that allylic lone pair pattern. And we can continue on and draw this several more times. Because the lone pair, when it's involved in resonance, makes it aromatic, and that makes it a lot more stable, it's not available to act as a base. Because most of its time is spent in resonance in the ring. Okay? So, aromatic. That was weird. I tried to write it right. Didn't quite come out. So one of the rules is, right? So if a heteroatom's lone pair is necessary, it's included in the Huckel number. That's the number of electron pairs to make it aromatic, right? Then it's not available to act as a base. In pyridine, the nitrogen has this double bond to the other carbon, and it also has a lone pair out of here. So it already has one pair involved in the aromatic ring system. The other pair can't be involved because it's not in the correct orientation in the molecule. Remember, to be in part of the conjugated system, right? This pair of electrons has to be vertical, and this one's horizontal in the plane, okay? And if you included this one, it would give it an even number of electrons, making it anti-aromatic. So if you look at the pKa's, right? Aromatic, this is non-aromatic. So what ends up happening? So this is aromatic, right? Because this pair is involved in resonance. It becomes a lot less stable when you protonate it. So it's a much stronger acid. It wants to get rid of that proton and become its stable conjugate base again. Pyrrole, on the other hand, when it picks up the proton, right? The pair of electrons in the nitrogen involved in the pi bond are still involved in the aromaticity. And so it doesn't matter as much whether or not it picks up that electron. Another indication of like how the electrons are distributed in the molecule are those electrostatic potential maps that we make in lab all the time, or used to make in lab all the time. And if you look at the electrostatic potential map of pyridine, all right, you see a lot of negative charge on one end. That means the electrons are localized to the nitrogen atom. Whereas if you look at pyrrole, the negative charge is actually distributed towards the pi bonds. Right? Indicating, though, that the electron charge is distributed in the ring. Again, a sign of aromaticity or resonance.
Can you repeat that?
I don't know. Okay, so electrostatic potential map, right? Green and blue are towards the green is neutral, blue is positive, red is negative. So you take an electrostatic potential map like this one for this molecule. You'll notice it has a lot of red here. Okay, anytime you see a high charge in one area, that's a like negative charge, that's a localized charge.
Okay.
All right. Well, resonance is like delocalization, right?
Yeah.
So when you look at pyridine, it has one lone pair. That charge stays here because this pair is not involved in resonance.
It can't be.
Can't be, right? And then in this one, this lone pair, even though it looks a lot like that one, when you look at the electrostatic potential map, you notice it's actually positive on this end. It's because the nitrogen's pulling electron density away from the hydrogen. But also the electron density is delocalized around the conjugated system.
So it's distributed across the molecule. Right?
Yeah, because it's involved in resonance. Yeah. All right. Aromatic, anti-aromatic, or just not aromatic? First one, we'll go with molecule 1. This is kind of like a lie. That's okay. Aromatic, anti-aromatic, or non-aromatic? Huh? Neither. Why?
It's just not involved. The lone pair can't. There's no resonance.
That's part of it. The lone pair can't be involved. That's one. But the other thing is, it's an 8-membered ring. 8-membered rings aren't going to be flat. And we talked about this the other day. So it's like cheating. That's why I said it's like cheating. So it's non-aromatic because it's not flat. What about this one with oxygen? Now that's a 7-membered ring. Right? Aromatic, anti-aromatic, or non-aromatic? Well, it can't use both. Oxygen can't use both lone pairs. But it's sp3 hybridized, right? It's got 2 lone pairs and 2 bonds. So if it uses one of the pairs of electrons and involves it in resonance, then it'll be anti-aromatic because it'll have 4 pairs, right? So here's the thing. If a pair of electrons can be involved and make something aromatic, we use it because it's going to be more stable when it's involved. But if it's a pair of electrons and it makes it anti-aromatic, it's not going to participate in the resonance. So this molecule is also non-aromatic. Sorry. So what about the number 3? I told you these are like kind of weird, but it involves some analysis. So the first one, non, because it's not flat. So the first rule, Huckel rule, isn't followed, so it can't be anti-aromatic or aromatic. Second one, right? This one's also non-aromatic because involving one of the pairs of electrons would make it anti-aromatic, so it won't involve the another pair of electrons. So the oxygen remains sp3 in the system. What about number 3?
I got a question.
Yeah.
So any sp3 hybridized molecule with 2 lone pairs will be non-aromatic?
Unless one of the lone pairs can be involved as an odd number of electron pairs. The key is whether or not it's going to have an odd number or an even number. So if that oxygen was in a different ring, so for example, it was in this ring. I don't know if I can do this or not, actually. Let me see. Back up, too many carbons in this ring. What would that be? Well, right now the oxygen has 2 pairs in it, right? Like this. Looks angry. So it's got 2 lone pairs on it. So it's sp3 hybridized, right? So if it doesn't participate, it's non-aromatic. But if it does participate, what happens? It's aromatic. Because when this pair gets involved in resonance, right, it has this odd number, so that one's aromatic. So this is an example of what it would be if it was aromatic. This one's anti-aromatic or non-aromatic. Because if it includes it, it's anti-aromatic. If it doesn't, it's sp3 hybridized, so it doesn't conjugate that oxygen. Okay?
When it's involved, what do you mean by the odd numbers of electron pairs?
I mean odd numbers of electron pairs. 1, 2, 3. All right. This one right now is even. Oops, that's not what I meant to do. Oh, see what you made me do? Your fault. This one's even right now. 2, 4, 6, and if you used one, it would be 8, right? And that would make it anti-aromatic. Because it would conjugate the whole ring. It's only 7 carbon, or 7 atoms, so it would have to be flat. Okay? So it doesn't include it because it would be anti-aromatic. Anti-aromatic means it's a lot less stable than you predict. Okay, so this one is going to be what?
Isn't it over?
Yeah, that's a tough one.
Why are you giving us rules and then break the rules?
Hang on, let me go back. Just double check something real quick. So let me back up. Why isn't aromatic, anti-aromatic, or non-aromatic? What did we decide? Well, it would be anti if you included all 4 and it was completely conjugated. So what the molecule does is it folds, right? It folds to break the conjugation, so it actually ends up, even though it could be flat, it's not, because it would be anti-aromatic if it was flat. So the molecule, the energy, just that energy of being anti-aromatic forces it to be folded and breaks conjugation because it's unstable. Here, if you include this pair, what's that going to do? It'll be aromatic, so it'll flatten out. To include the pair to be more stable. So that's the difference between like the rule. I know I said the rule and it sounded really easy. It's not going to be flat. But if it can be flat and aromatic, it will be flat and aromatic. This one? No, because there's a hydrogen missing here because of the negative charge. Right. So if the simple rule is if the pair can be involved and it's aromatic, then it's going to be aromatic. If it makes it anti-aromatic, it just won't be involved usually. Okay. So what about this one? How many atoms in there? 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what's it going to do? It's going to bend to break the anti-aromaticity. Yeah. Okay, there's lots of other. Sorry. Shouldn't laugh. Just going to throw this in here for fun. And get rid of that. What would that do? Aromatic, anti-aromatic. Huh? Aromatic, because we'd use one of the pairs from the oxygen, include it in the resonance structures, and it would flatten out because it makes it more stable. Yeah? So if a pair can be included, it doesn't matter if it's oxygen or what, if a pair can be included and makes it aromatic, then we include it. Okay. These are all examples of polycyclic aromatic compounds. Your first introduction to these was probably barbecuing. You find these all over the place when you barbecue. They call them the abbreviation, okay, because not that it's that important. I don't care if you know this, like, for this class, is PAH. They're PAHs. Polyaromatic hydrocarbons are found in all kinds of things that you barbecue. Why do you find them in things that you barbecue? Because of charcoal. And when you burn stuff, a lot of these compounds will form. Okay? Do you think they're good for you? No, they're not.
They taste good.
Man, they taste good. Yeah. All right. So we talked about stabilization energy, right? Benzene has 52 kilojoules of stabilization energy. We talked about that in that hydrogenation slide where we said, oh, here's one double bond, here's two double bonds. This is what benzene would be if it had three double bonds, but in reality, it's this number, and the number was 152 kilojoules per mole lower than you predict, right? So naphthalene, right? 255 kilojoules, anthracene 347, phenanthrene 381 kilojoules of stabilization energy. A lot of stability gained by aromaticity. Okay. Per ring, I don't know if it matters very much, but it's a lot lower than benzene per ring. But they've got a lot of rings, so it's a lot more stability. Okay, so let's show how these things meet Huckel's rules, right? Fully conjugated for naphthalene. Every carbon is sp2 hybridized. How many electron pairs? 5, so it's aromatic. These rules work really good up to 3 rings. That's why they stop at 3 rings. And when you get to 4 rings, it's kind of like, well, you can make them in ways where it's hard to tell that it's aromatic. Anthracene, all right, 3, 5, 7. Continuously conjugated, it'll be flat to be aromatic. And then phenanthrene, continuously conjugated. Now you guys know what I mean by that, right? It's every carbon has a double bond touching it, or every atom has a double bond touching it. So 2, and then 3 more, so that's 5, and 2 more is 7. Okay, so odd number of electron pairs. So those are all aromatic. Okay, I'm going to switch topics a little bit. Start talking about reactions that you expect to see at benzene. Oh, by the way, your reaction notebooks are up here too. And before I forget, a couple of people didn't give me reaction notebooks. So the summaries are there. I'll give you your exams later. The carbon next to a benzene ring is called a benzylic carbon. Okay? And the thing that's interesting about benzylic carbons is that they're really easy to make radicals at, and they're really easy to make carbocations at. The reason is because the charge can be delocalized into the ring by resonance. Okay? So if you try to oxidize benzene, benzene's very stable, it doesn't react. That's Jones reagent, right? If you try to oxidize an alkane, a saturated hydrocarbon, right, no reaction. But if you try to oxidize an alkane attached to a benzene ring, it'll cleave at the benzylic carbon. That is, this carbon, right, is the one that stays, the benzylic carbon stays, everything else gets chopped off, and you get a carboxylic acid. Doesn't matter how long the chain is, or what the things are on the chain, it is just going to chop them off. Okay? It could be on benzene, it could be on anthracene, phenanthrene, any of those aromatic compounds. Those aryl attached carbons are very easy to oxidize. On the other hand, the same rule applies that you learned before for oxidation of carbons. If it's tertiary, there's no reaction. So those tertiary carbons will stay.
So tertiary benzylic carbons will stay?
Yeah. So for example, just for funsies, for me anyways, if I have this, and I do like Jones reagent. Okay, I can't. Jones. Is it going up there? Okay, good. What's going to happen? This one's going to get cleaved, and this one's not. This is going to be a carboxylic acid. I'm pretty sure this ends up staying as a carboxylic acid, right? It's going to split at that point, so you can cleave it off. But the other side doesn't oxidize. So you can oxidize one side up, but you don't end up oxidizing the other side off. Okay. You can do the same thing with potassium permanganate. Advantage is it's not you don't do it as acidic, or you don't have to do it as acidic. Jones reagent has concentrated sulfuric acid mixed into it, so it is by definition very acidic, right? And then you get a carboxylate ion, which you can then protonate and get to a carboxylic acid. Mechanism for these, I don't know them. You don't know them. They involve radicals and lots of steps, and I've never bothered to learn them. It's one of those things that one of these days when I have some spare time, yeah. Okay. So what happens when you oxidize this one?
One of them doesn't react.
Actually, there's no tertiaries on there, right? If you look at this structure closely, there's a hydrogen here. There's 3 hydrogens here, so this is a CH3. So as long as there's a hydrogen there, it'll cleave it off. Okay, so when you do Jones reagent on this, you'll end up with this. And again, the reactivity has all to do with stabilization, being able to take the charge or the radical and stabilize it through the benzene ring. Okay. We learned that bottom reaction, NBS, for allylic substitution reactions, right? You could have actually just that molecule and it would do the same thing. But with the benzene ring, benzylic and allylic positions have a lot of the similar chemistries. And then once you make the modification at the benzylic carbon, there's a lot of stuff that you can do with it. For example, if it's a primary, you can do an SN2 reaction. If it's a tertiary, it can be SN1 and produce alcohols. And you can also form alkene. Once you get the alcohol formed or the alkyl halide formed, it's easy to form an alkene from that. So there's just some synthesis things that you can do.
Dr. Count, the previous one, were they carboxylic acid that was formed, or was it?
Oh, the one I drew?
Yeah.
Yeah. Oh, I'm missing an O, huh? Yeah, I'm missing that O. There. Okay. I think we're just about to the end. Yeah. Okay, so some of the reactions, like transformations, you need to be familiar with. They make these slides for you in the back of your book. All right. If you want to modify a benzylic position, you can do radical bromination. You can use MBS. You can use BR2 and light. There's a bunch of things that you can do. It'll only modify here. The benzene ring's too stable. And then from here, you can do SN1 or SN2. You can also do oxidation. So if you have either a secondary or a primary, you can oxidize that to carboxylic acid. Remember I talked about before, you can also, hang on. Our friend SOCl2. What does SOCl2 do? Replaces something with a Cl. Yeah, and it'll do the same thing to carboxylic acid. So you can also make acyl halides out of this, which we'll find out in the next few chapters. They're very reactive, very useful for synthesis. Okay. Anyways, bunch of things that you can do. So let's do a little practice. Okay. What are the reagents you would use to do each of these modifications? So let me label these so we can all be on the same page. How do you do A? You do BR2 NB or NBS, right? Because it's a bromination reaction, so there's tertiary carbons here, right? So BR2 what do I always call it? I lost the word for it. Substitution, anyways. Right, reactions, radicals, there we go, radical substitution reactions. You use BR2, but it's also benzylic, so you can use NBS. So either one of those will work. I'll fill that in. Or NBS. Light or heat, some radical initiator. How do you form this ring? Huh? T-block. Yeah, very strong base. In fact, any good, strong, bulky base will work. In fact, any base will work because they're tertiary carbons. That's basically all you're going to get is elimination. But we like T-block because it sounds cool. Sounds like a rap singer, huh? Sorry. All you Tupac fans. How do you go from here to here?
Magic.
No, it's not magic. Let me ask you a question. How do you do D? Jones reagent? Yeah, chromic acid oxidation. So you do this one by chromic acid oxidation. So I'm just put Jones here. You can also do it here. So chromic acid oxidation on either one. Doesn't matter that it's not benzene now. It's an aromatic ring system, right? Any carbon at that position is called benzylic, and you can oxidize it. Okay. So just a couple of things to keep note of, because remember we talked about benzene being really stable. So if you try to produce cyclohexane from benzene, the activation energy for hydrogenation is extremely high. So if you want to reduce a benzene ring, you have to use a nickel catalyst. You have to go to 100 atmospheres. That's a lot of pressure, right? And at 150 degrees Celsius, and then it gives you 200 kilojoules per mole, basically, and you can get cyclohexane. But for the most part, that's the only way to reduce a benzene ring to cyclohexane. Why is it so hard? Because benzene's really stable. So anything you do to it requires a very high activation energy. Okay. On the other hand, that can be useful because if you have an alkene attached, a styrene, right, vinyl benzene, and you want to reduce the side chain, it's very easy to reduce it and not reduce the benzene ring. You don't have to even be 2 atmospheres. You can probably do it at room temperature and at atmospheric pressure. Okay. Questions? Just basic transformations. Okay, this is one of my favorite. Oh, sorry, we didn't switch slides. I like this reaction. It's called a Birch reduction. It is one of the easy ways to get benzene not to be benzene anymore. But because benzene's so stable, you have to have a very reactive reagent. And so what we use is sodium. Okay? So sodium, it's a radical reaction. The mechanism shown here where the sodium donates electron to one of the positions. That causes rearrangement of the pi bond to produce a radical here, and this is an anion here, so we call these things radical anions. It's done in a solvent like methanol, and so what ends up happening is that the pair of electrons then attacks the methanol to make methoxide, and then a second sodium is involved to reduce this radical here, and you end up getting an anion, which then can pick up another hydrogen, and so you get these really neat little structures that look like this. I have to admit, one of the reasons I really like this reaction, it was involved in one of the really super catastrophic industrial disasters in the Birch reaction, and it was caught on video, so it just basically looked like a hydrogen bomb went off. Because to do this, I know, maybe I shouldn't be so happy, but it's a very good lesson, I guess, in chemistry. What they had done is they wanted to do this Birch reduction process on an industrial scale. You can do this in the lab, right? It involves sodium, and then the sodium reduces the benzene to this diene, right? And then you can modify that and do other things to it. Anyways, so they wanted to scale it up, and so what they ended up doing is they scaled it up to a really large scale. It involves molten sodium, though. And the reaction's exothermic because you're breaking a pi bond. And so it got out of control. And so then the sodium converted all the solvent into hydrogen gas and then just exploded. So if you look it up, you can find it. I think if you look up Birch reduction disaster, you'll find it, the video. Anyways, so interestingly is if you put an electron donating group, an R group, on the alkyl side, then what ends up happening is this is the structure that you get, and you don't see this structure. So it's a regioselective reaction. I haven't worked this out in a long time, so let's try it. So if the sodium is here, I'm going to draw the sodium in. I won't do the whole thing, but I'll get it started. Oh, shoots. I have a sodium here. Let's see. Yeah, so let's do it like this. If the electron adds here, what's going to happen? This pi bond breaks, so one side goes this way, and then the other side goes to here. And then in the Birch reduction, this goes like this, right? And this one goes here. So there's a whole bunch of little arrows involved. That's going to give you this. Right, you see how that worked out? So that's the intermediate, okay, that leads to the product that's not observed. If it's an electron donating group, so like an alkyl group, why don't you see that intermediate form? Why don't you get that product that's shown there that says not observed? Well, yeah, it's not stable. I mean, that's the kind of the answer to one of those. I know. Well, the answer is this one's formed because apparently it's more stable in its intermediate than this one is. But if this is an electron donating group, then the R group is donating a negative charge to this carbon already. So this is going to be high in energy, or higher in energy. Look to see what happens if you add it to the other end of the bond. Okay. So now I'm going to erase, and I'll start over. I've got to figure out which one's my eraser. Is that my eraser? Let my kids draw on this, and then I don't ever know what's what. So now I'm going to have the sodium attached to the other side. Oops. And then what you get is this intermediate. Right? So the negative charge isn't where the electron donating group is now. Right? And this leads, oh, I drew it backwards, darn it, to that product. Flip the ring around. So because the negative charge isn't where the electron donating group is, right, that's the major product, because that pathway is going to be faster because it's a little bit more stable. Let's say you want the orientation to be different of the double bonds. What do you think you have to change to get the reaction to go through a different pathway, preferably? So right now, right, you have the substituent that's on the ring in the vinyl position. If you want it to be allylic, if you want it to be like this instead, what do you think you have to change about what R is? No, it's withdrawing, yeah. So if you put an electron withdrawing group there, then the orientation of the bond switches, so you can control the way the double bonds are placed with the substituent on it. Okay. Anyways, I think it's a cool reaction, which means you should know the mechanism, because I think it's a cool reaction. Make a big red star. So, example, right? Electron withdrawing group, carbonyl group. Unfortunately, they don't give an example electron donating group, so you could be like a nitrogen donating group, like an amine or something like that. Just a little bit on spectroscopy. I was going to do a little more on this. I don't feel like doing it now because there's not much to talk about. A couple of things. In the NMR spectroscopy, or in the IR spectroscopy, between 3,000 and 3,100, here, let me just show you. Here, and then I'm going to draw a line up from 3,000, like that, but I'm going to use a different color because that is red. Hang on. Lavender? You can't see that either, huh? Oh, I know. Nope. Sorry. I didn't think about this slide being so horribly miscolored. There, that's better. Right? What do you normally expect to see to the left of 3,000 on an IR? Yeah, there's some aldehydes, but it's carbons that are double bonded, sp2 hybridized. Because the bond is shorter because it's sp2 hybridized, those stretches tend to be higher in frequency. So you tend to see, in this region over here, these vinyl hydrogens. Okay? Everything between 3,000 and like 2,700, 2,800 is typically associated with, sp3 hydrogens, aliphatic hydrogens. Okay, next thing to point out. So these are usually pretty weak. They're they call them combination bands and overtones. There's a bunch of things that are here, but from 1700 to 2000, okay, that's these guys here. That's what you see when benzene usually see when benzene has one substituent on it. A set of evenly spaced peaks that are either overtones, which means higher frequency bands that you see over here, or combinations of frequencies combining and you see these other peaks. Anyways, doesn't really matter. Diagnostically, you can tell that benzene has a single substituent by seeing 4 peaks there. In your book, I don't remember if I put it in the slides. Hang on. No, I didn't. In your lab book, let me go back to this. Okay. They show that if you have 2 substituents or 3 substituents, and you can see these peaks, you can tell the substitution patterns based on the patterns of these peaks. Okay, I'm not going to make you memorize that, but you should know how to use it. Okay. If you need it for an exam, I'll give you the chart that has that in it so that you can say, oh, it's got a peak here and here, so it's got a 1-3 substitution, right? You don't know what's on what position, but you can tell like where the substituents are on the ring relative to each other on benzene. I didn't realize the CC double bond peak was this big on ethyl benzene. But these are CC stretches. Okay, so going again. Oh, there it is. Sorry, it got jammed. CC stretching, okay, 1415 to 1650. So you'll see those in a lot of the NMR benzene rings. Okay. Now, like for the experiment you're doing now, you're going to have that, but it's not a big deal because you started with a benzene ring, and there's not much we can do in a lab to undo it unless we like add sodium or something like that. But it's good to know that that's what those are. Okay. So there's also what we call in-plane and out-of-plane bending. So I'm a benzene ring. So am I? What's my geometry if I'm a benzene ring? I'm flat, right? So in-plane stretching is like jumping jacks. Okay, that's what they mean by that. You don't need to know that stuff, but this is the frequencies that you typically find them in. And then out of plane is like when you do twists like this, where you go like this. And you're flapping your wings, right? If this is the plane, these are the movements. Oh, shoot. Okay, so, yeah. So these are examples of the CH bendings. If you don't know you have benzene, then what you do is you look for a combination of these peaks, and then you try to build a case that there's a benzene ring in the structure. Okay, NMR. So if you remember, double bonds cause peaks to shift. We call that anisotropy. It's the electron cloud of a double bond causes things to shift downfield. So again, this is proton NMR. In the region between, and I always just tell people between 6 and 8. It's a pretty big region, I know, but it depends on whether there's electron donating or electron withdrawing groups on the ring. Again, this is for ethyl benzene, right? Hang on. These peaks, okay. That didn't sound good. Sounds like somebody was violent in the bathroom. Okay, now, or the adjunct office. Actually, they're the same thing. So, so there's 5 hydrogens. No, it's a bad joke. Is there something going on out there? 5 hydrogens here, right? This CH2, where do you normally find CH3 and CH2? Usually find them around between, CH3, you usually find it around 1. CH2, you usually find it around 1.4. So there's at least a 1 part per million shift caused by the benzene ring. And because it's a fairly large electron cloud in the benzene ring, even this group is shifted, even though it's 2 carbons away. So it's a fairly large field that it creates, okay? In the next chapter, what we'll do is we'll get into actually how does the substitution pattern on benzene affect what you see over here, and that's actually the stuff you'll need for the report that you'll be working on for next week. So, all right. So, carbon NMR. Oh, sorry. There's a couple of things I should point out. These are easy ones to do. If the molecule is symmetric, then each one of these hydrogens is exactly the same. So you would see one peak, right? 4 protons on it. It turns out if it's asymmetric, that is, you have an electron withdrawing group on one end, an electron donating group on the other, or 2 electron withdrawing groups that are different, then what happens is these 2 hydrogens behave the same, and these 2 hydrogens behave the same, okay? But then they're coupled to each other, and so you end up getting this split into a doublet, and you get this split into a doublet. So when you have this substitution pattern, a pair substitution or a 1,4 substitution pattern, what you see is what we call the doublet of doublets. Like it's 2 doublets next to each other. The one that is further downfield is closer to the electron withdrawing group, or the stronger electron withdrawing group, and the one that's upfield to the right is towards the electron donating group, or the one that's less electron withdrawing. Okay? So if you look at it, these 2 patterns are very easy to spot if you have them. In fact, a lot of your starting materials for the experiment you're doing right now only have a single substituent, and when you run the NMR, you'll see it just has a single substituent, because you'll have all 4 hydrogens in a single peak. I'm sorry, 2 substituents. So there's xylenes. If you have a single substituent, it looks like this blob that you see like this. Okay. So carbon NMR is real nice. There's a lot you can tell from carbon NMR. If you have 2 substituents that are the same, like this, there's only 2 peaks that are produced because this carbon's the same as this one, and this one's the same as that one, and vice versa as you go down this way. So there's a lot of similar signals. If you have 2 substituents and they're in the ortho position, you end up with 3 because of the symmetry left and right, right? If they're different, then you end up with 6 signals. And then if it's para, 1 and 4, and they're different, you'll end up with 4 signals because the left side, top side, and the bottom side are the same. Okay? So just some interesting things to think about. We use depth in our analysis, so you can tell how many carbons have hydrogens on them, right? So it turns out if you use that information and you use this information, you can usually determine what the substitution pattern is on the ring. Okay. Doesn't take that much. Okay, I'm going to skip this section. I'll let you look at it. It's got all the answers worked out. These are everybody's favorites aromatic compounds. This is known as a carbon nanotube. And basically it's a long cylinder. And what do you see in here? It's a benzene ring. So it's a benzene ring. There's actually no hydrogens on it. It's pure carbon, right? And it's double bonded in such a way, like if you were to draw it, see if I can start this and not blow it. I don't know. That if you go through the structure, it's continuously conjugated, and it's large planes, large sheets of material, and no hydrogens on it. Okay, so turns out because of that, they're electrically conductive and very strong structures. But anyways, a lot of fun applications of these things. All right. That is that for that chapter.